Well, thanks a lot for the introduction. I am Sean Park, and I am actually from. So I'm actually from Australia. Yeah, but in fact, I was born in South Korea, but I live in Australia, and I'm a Australian citizen at the moment. So, just in case that you wanted to know. So the topic that I'm going to talk about today is neural blacklist. So the world has changed ever since the dawn of the computer, and the world has even more changed ever since we've got the invention of the internet. And now the world is going to go through even more dramatic transformation because of the artificial intelligence. So, for example, we've got deep learning, techniques that can translate the Chinese characters in the picture into the English picture. So that's all implemented in using deep learning. Also, using deep learning, you can recognize the objects in the video, the persons, the motorbike, the tie, and chair. And even, we get frustrated by the AlphaGo, as a top player in the game of Go, you get defeated by the machine. And these days, we got something called StarCraft 2, which is a video game, and who knows that one day the machine can defeat the human players. So yeah, so the whole thing is about deep learning and artificial intelligence. But so the question is, how can we use that sort of a cutting edge technology into our security problems? So I have been working on a lot of those AI projects up until now, and so this is the topic that I'm going to talk about, and that's it's only one of those projects that I'm working on at the moment. It's called neural blacklist. So, in the old days, we used to get the calls from someone, from your colleagues, or you just get some information about the outbreak of the malware in the websites and things like that. And you just manually enter the details of the malicious URLs into the blacklists, so that way you can just block them, from being accessed. And as you know, the malicious URLs are one of the major threats in the security world, because in the malware campaigns, you've got infection chains. You've got at the beginning, you will be infected by simply accessing the initial infection site, and once your computer gets compromised, the malware will be accessing the drop site and the CNCs and the payment sites, etc., etc. So it's very important. It's very important to actually block and detect and block those malicious websites. But today things have changed a lot. So in the past, the volume of the URLs and the style of the URLs were very manageable. We could do that manually, fully manually, using your intelligence and your fingers on the keyboard, right? But these days, we've got a bunch of those malwares, and we've got too many URLs. We've got too many automatically generated URLs. It's like that. So it will be humanly impossible actually to, add all of them into your blacklist, really. And besides that, what you're seeing is only just half of, it's not half actually, it's only in tip of the whole, volume of the URLs, that malware can generate. So so what that means is, even though you actually have added all of them in your blacklist, it may not be perfect, because tomorrow morning, the malware may access other websites, other URLs, which is also, automatically generated. So how can we handle that? Before we go straight to the solution, let's have a look at each one of those really, tricky URLs. So, for example, the crypto locker is one of those, was one of the major threats, and I think it still is. And if you have a look at the URL pattern, there you've got the initial domain name / and you've got the random folder name. We've got another random file name .php $ID equals person's email address, and the person's email address is usually in the format of the first name dot last name at etc. So and it's hard to detect the kind of URL pattern automatically, or even using your regular expressions. It's very hard because we've got the random names in there. Another one that has been really popular this year is Loki. Loki is also just another ransomware. Loki version 2 is using something like that. So the format of the URL looks pretty much like a DJ, the domain generation algorithm. So the way it works is just like this. The malware has got its own algorithm embedded inside. So every day it automatically generates a new name, a set of new names, different names like that. And at some point later, when the attacker decides to activate the attack, before that, all those names will not be resolved if you, put a DNS request on those domain names. But at some point, when the attack activates the domain by simply registering an IP address associated with that, then it will get activated, and the attack will actually be further initiated. So, and that's the idea of the DGA. So because using the algorithm, you can generate like billions. It's not. You can generate millions of those URLs, or it can be billions of URLs. Who knows? And it's just simply impossible, or even though if it's possible to add all those names in your blacklist, it's just just waste of space essentially, because all those domain names are not active most of the time. So it is just really pointless. And also we've got a rig exploit kit that has been really gaining the traction early this year, and it has been really successful in the attacks. And it was delivering the server ransomware as a payload. And I think also it has the capability to actually just deliver the other types of malware as well. So if you have a look at the format of the URLs it's using for accessing its payment side, it looks like that. So it's got, again, appears that it is a DJ name. In this case, we've got some numbers in the domain names as well. So, how can we add that sort of stuff? How can we detect the URLs like that? That's the main problem. So, as a human being, we are a very intelligent species, right? And by simply looking at the pattern like that, we need only a few of those examples, and we can automatically identify whether this particular URL is a RigEK URL or the Loki URLs. We can automatically, identify it really accurately. So how can we actually, achieve that? by using the machine. So, right. So I mean, to summarize, the problems. We're living in the sea of the URLs every day, and how can we identify these URLs automatically? So in the past, people have been using a few of those machine learning approaches, like support vector machine, random forest, and lately, XGBoost. So if you have a look at the code up there, on the top, you've got 3 sections there. At the top section, we just a couple of lines of code to read in the data set, and in the middle section, you've got the training function invocation, and at the bottom, you simply doing the prediction. It's just only a few lines of code. Anybody can do that, right? Even if you don't have any experience in the machine learning field, if you really understand the whole concept, you can do that easily. And the way it works, it doesn't matter whether you're using XGBoost, SVM, or random forest. The idea is that the input is going to be some sort of a tabular data structure. So you've got the fields, like for example, some fields, the frequency of some alphabet A, frequency of alphabet B, frequency of alphabet C, and things like that. So you just create your own features. Or alternatively, you can simply use n-grams, a unigram, a bigram. So what it simply means is just the statistic, the frequency of some numbers in the URL. So you can use that sort of approach as well. In fact, if you've got experience in the machine learning space, you almost always use n-gram approach because it's easy to apply, and it has been used a lot in the past, and there has been a lot of success stories reported as well. So, and that's part of the reason why you use n-gram models. And if you, so after the training, you will be able to see the decision tree, built up internally inside the algorithm, and it will be looking like that. So you will simply, for each features in the input vector, you simply, so depending on the value in the input vector, you will get if else this one, if else that branch, if else that branch, right? So it's just simple stuff like that. So it's pretty easy to understand. However, the main reasons why it has been used so well and a lot by the engineers is because it's easy to program, in my view, and it's very fast when you're doing the training, and it's also very good if the input feature is well defined. If input feature actually makes sense, if input feature makes sense, and also it's fun because you're using your brain, human intelligence. I want to implement, some fantastic feature like this. I want to do this. I want to do that. You can use you can meet your programming, desire, I guess, in my view. So I'm not saying that it's an entire failure, but what I'm saying is it has flaws in it. And I've just summarized a few of those flaws at the bottom. But the main thing is, how about this? Okay, so I've spent a few days to implement a feature, set of features. So in fact, initially I tried n-gram model at the beginning on the URLs, and it seems like it's working. It's achieving just 80% accuracy, for example, right? And it's not enough. So you try your own features. You invent your own features. Some sort of, for example, how many slashes you've got in the URLs, for example, right? And you can increase the accuracy on top of that too. So it may increase the accuracy, but it's not really, nowhere near the, a perfect accuracy. So, and the bigger problem, the only single biggest problem in that approach using XGBoost, SVM, random forest is, okay, the features I have invented is working for this particular URL types. And the next day, you've got a new malware campaign, a new family has appeared, and they're using a completely different URL pattern, and your feature does not work. So in that case, we have to spend another few days to invent another features. Are you going to do that? I wouldn't do that. So that's major motivation for deep learning. Deep learning is, has been inspired by the human brains, of course, and it has neural network. You've got the neurons and the activations and the weights, synapses, and usually we've got the input layer on the left-hand side, and we've got the output layer on the right-hand side, and also we've got the multiple hidden layers in the middle, things like that. And of course, the major, the core ingredients of the neural network is the nonlinear activation against the weighted sum on the inputs. So I'm going to give you just a bit of a quick demo on the results. Sorry, on the training and the results first, and I'm going to move on. Got 33 minutes left. So the training, I'll show you. Well, can you read it at the back, actually? Is it too small? I will make it a little bit bigger for you guys. Hopefully you can read that. Okay. So I'm using basically a TensorFlow. And as you can see there, you've got the epoch. At each epoch, you can see that the cost is going down. No, actually, it's not going down. I don't know why. But I mean, it fluctuates sometimes, but it will eventually drop. So, and also the mini batch accuracy will increase over time as well. I've got 100 epochs, so we can wait until it will be finished. The patience is the virtue in this world, in the machine learning space. You have to learn to wait first to get the results, right? But anyway, I'm going to stop right now because I'm not going to wait. Just stop right there, and yeah, I'll come back later. So I'm using the trained model, and so I've got the URLs. Actually, I need to show you what the URLs look like first. URLs is right there, that one. Yeah, so it will look like that. Again, it's pretty small. So it will look like that. You got a few of those. So we have no idea. We got like millions of those URLs incoming in EchoMyLog every day, if it's not billions, right? And how do you know? How do you know? I mean, it's just too many URLs out there. So if you just run the trained model, you can see that it has the capability to detect all those hard to detect URLs. Let's wait. There you go. Just a few of those samples there. So you can see that in the green, sorry, in the yellow, Oops. And up. Okay. In the yellow, it has detected the crypto-locker URL. As you can see, it's obviously the URL from the crypto-locker. And in cyan, in green or blue, you've got the locky URLs, which is the DGA URL. In red, you've got the server payment site URLs. So yeah, that's what they can do. That's what the deep learning is able to do. Okay, let's get back to our slides. So I have used something called RNN, the recurrent neural network. So it has one single memory cell. Just imagine yourself, you're a human being, right? Your brain, you think over the time. We have got in 4 dimensions. We've got X, Y, Z, and the time. So we have got a new perception of your world, and at each time step you get new inputs, right? You've got a new person incoming, you've got a person leaving. So each time you get some sort of new piece of information. But at the same time, the whole thing, you maintain the memory image, essentially. And that's the whole idea that RNN is exploiting. So we've got a single cell, and the weight will be simply updated. So, when you say, I'm training a neural network, what it means really is simply updating the weights between the neurons in such a way that it will, give you the right results. So if you just unroll that cell, it will be looking like this. So at each time step, your memory cell state will be updated based on the previous memory state and the new input at that step. And at the end, you want to get the answer. So you have seen xyz.com.tw. What would be your answer, right? And that's the model that we've got. So if you just zoom in, between the cells, it will be looking like that. So as I mentioned before, it has weights between the cells, and the weights will be just reused over time. And also we typically use hyperbolic tangent function as a nonlinear activation function. But if you simply do the weighted sum between the input vector against the weights, it doesn't have the nonlinearity in there, which actually is quite a bad thing in making the correct decisions in the longer term. So, and that's the reason why we always apply the activation function, some sort of a nonlinear activation function. And for RNN, we use a tanh function. I'm going to explain about the characteristic of that activation function later. So if you have a look at that particular state at the final state, right? And the things we want to get the answer, right? So we've got the memory states. The memory cell has neurons in it, and we want to convert that into the answer. What is the answer that we want to get? The answer we want to get is whether it is a clean URL or a crypto-locker URL, locky URL, or a server URL, right? So we've got the labels, right? So we've got 0, 1, 2, 3. We just simply assign the numbers for each one of those patterns of the URL. So how would you do it? How would you just convert the because for example the number of the neurons that we've got in the cell is usually bigger than the number of the classes that we want to classify, right? So we simply have a fully connected a layer between the memory cell and to the number of the neurons that which is equivalent, which is the same as the number of the classes that we want to get, right? So we've got 4 classes there. We've got 4 neurons up there after the fully connected layer, and after that we just apply the softmax layer. So what that is goes here. The output of those 4 neurons will be some arbitrary numbers, and what we want to get is we want to get the the probabilities of each class. If for a given URL, what is the probability of this URL being a clean URL or a crypto locker, right? So we simply apply the information theoretic probabilities. And some people ask, why are you using something more complex? He's like softmax instead of using a normalized sum and average and stuff like that. The reason for that is it has got some information theory being embedded in it. So the more error that you've got, it will be the probability will be a lot just lower and a bit just higher value at the input. It will actually push the probability a lot higher. So it is just a nonlinear transformation. Right. So after that, we get the actual probabilities of each level being accurate. So clean 0.1, 0.2, 0.1, and 0.6. So in the case, it will be the server URL, right? And okay, so we have got the architecture of the model, but how can we do the training? We're using something called backpropagation. Backpropagation has been around for a long time. That's not a new idea. It simply computes the error, which is the difference between the label and the desired output. And then we simply ask at each layers, whether these particular activations are actually affecting the error or not. And after that, we just go back again one step further, and we just see whether a particular weight is affecting the activations of the neurons or not, and so on. So it simply goes back all the way to the input layer. So we got something. Up until now, it looks like everything is fantastic. We can simply apply RNN, and we get the answer. Unfortunately, as the number of steps increases, you just forget, right? So I remember some stuff that actually happened yesterday very clearly. In about a week time, I may recall that a little bit. That happened about a week ago. But in about a year time, I may not remember anything, right? So it just happens here again in the neural network as well. So it's called the vanishing gradient problem. So the main issue is that if you have a look at the activations in between the cells there, the red line there is hyperbolic tangent function. So it has the y range of -1 to 1. So depending on the already sums input, it will just output either -1 or -0.8, 0 or -0.3 or 1, etc. Right? So the way the backpropagation through time works is it sees the gradient at each time step, and if it if the slope is small, then it will actually, correct the weights very slowly. Just assuming, because the hyperbolic tangent function will not actually reach number 1 or -1. It will go infinitely, right? So if your neuron is saturated, which means your activation will actually, the output of that hyperbolic tangent function will be far, far away to the right. Then it will be hard to, make a correction all the way back, because the slope, the gradient will become really small. It's really small, so it takes a long, long time to get all the way back. So it's called a vanishing gradient problem. So to just address that, people have invented something called long short-term memory. So it simply, has got some sort of just gates, like in the circuits, in the computer circuits, for example, you've got AND gate, XOR gate, OR gate, NAND gate, things like that, right? And so we just, devise the cell in such a way that when the backpropagation happens, it will, just memorize the stuff, or it will, forget stuff. So for long short-term memory, we've got 3 gates. You've got the F is the forget gate, U is the update gate, R is the reset gate. And one single, there are a lot of variants on LSTM, and one of the optimizations that other people actually made is called GRU. It uses only 2 gates, but still has the same effect as LSTM. And on top of that, so using GRU, I have achieved up until like 98% accuracy. Believe it or not. I'll give you the results, later, after a few slides anyway. So I was thinking to, improve the accuracy, and was, looking at the paper, which is at the bottom of the slide, and it was using something called attention mechanism. So the idea is simple. If you have a look at the picture, on the right-hand side, it is the mapping between the French sentence and the English sentence. So as you can see there, the activations are actually dependent on different characters. So if you look at every single one of them at the input, you may not have the accurate result. But if you are focusing on some specific characters, then you will get more accurate translation. And that was the idea that the person actually has researched on. So I have applied that. I'm sorry. Ooh. And it actually has increased the accuracy a lot too. So it looks like everything is perfect until now, but I realized that I realized something really important, and because of that, I could not really achieve the accuracy that I wanted to have. So it's called something called embedding. So if you ever look at the all the successes of the deep learning, what they have in common is the input has just smooth, continuous values. For example, images like this. Images like this if you have a look at each pixels, and if you have a look at the other picture that will look very similar to that, the distribution of the pixels in the input space are almost identical. Well, they're not identical, but they're very similar to each other, right? So the input is very smooth. But the problem we've got is we've got the URLs, the number of characters as an input. So each individual, the pixels have meanings. We can, find the differences and find similarities between the pixels. But the symbols, what's the similarity between alphabet C and alphabet A? Well, there's no similarity. And what's the difference between alphabet A and D? It has no meanings in its own form as a symbol, right? So what we want to do is we want to learn the representations of each input element, the input vector, by using something called embedding. We just assign numbers for each input, each possible input symbol. So it's called embedding. So with all of that, we got RNN, GRU, attention, and embedding. The final architecture is that. So that's the architecture I actually have used in my research. And I'm going to explain the hyperparameters of that. So I've used only two layers. So what you might wonder, how can you actually do that? So we've got just one single layer. But by simply feeding the output of the previous layer to the input of the next layer, you can have a more high-level understanding of the input state. Understanding of the memory state. So I have used two layers, and then of course I got the embedding layer, and also I'm using something called bucketing, because some URLs are very short, some URLs are very long, and if you simply apply the padding on a small URL, a short URL, it will take ages. It will take ages to do the training. So I have used simply put the small URLs into one bucket, and I've got the long URLs in another bucket, so that way we can do the training more efficiently. And also the cell type I used was GRU, and the number of classes I've got is 4. So I've used only 4 types of URL in this experiment. So I've got the clean URL, CryptoLocker, Locky, and server rig AK. And the number of hidden units I used in the memory cell is just only 64. So let's and people are asking, okay, so you have been talking about deep learning, and so what is the feature? What is the input? What does the input look like? And that's the answer. The biggest beauty I actually think for deep learning against the old style machine learning is we don't need to do the feature engineering. We don't have to spend hours and hours or days and days to find out what the right feature would be to achieve your goal. So the input is going to be just URL characters. So of course, the machine is not really understanding the alphabets, so it will understand the numbers. So we simply just convert the input URL to its number, right? So, and that's the input. And the data set I have used is I've used all were sourced from either Akamai or our mail operations team, or the ransomware tracker. So, and I've used a very small percentage of the samples for the training. I've used only just 10% of all the URLs. So I've got about 40,000 URLs in total. I've used only 10% of that for training. Okay, here we go. So we got the demo now. I think that's something that might inspire you guys if you haven't got any experience in deep learning. Show you that. Okay. Gonna start. Okay, so this is the a T-SNE visualization. So what it does is, so I'm just visualizing the hidden state, the the last memory state of each samples. So each dot here is representing each sample. And because the number of neurons I've got is 64, and I want to visualize on the 2D screen, so what Disney does is reduce the dimension from 62 to only 2 dimensions. And the colors are the actual labels, the actual labels of each sample. So the idea is to be convinced that your algorithm is actually working, you want to see clear separation between each class. So can you see, oops, sorry about that. Can you see the clear separation here or not? If you can see, give me a clap, please. So the blue dots here are just clean URLs, and the red ones are, what is the name of that? Let's have a look. I think that's Loki predicted name. Okay, in this case, the orange ones. Sorry about that. Predicted name, yeah. Okay, so that's Loki. Let's just go back to the label version. Okay, yeah, the red one is Loki, and the purple ones on the right hand side is server Reggae, and we've got the CryptoLaka there, and you can see the actual URLs of that too here. And that is the visualization for the training set, right? So what we're interested in is whether it will actually work on the real data set, right? So I have put aside a validation set, which is not, sorry. Okay, let's have a look at that. Which does not overlap with the training set, okay? Let's have a look at that just one more time. So I mean the fact that the points here are just clustered is not sufficient. It's not sufficient to to convince your friends that your algorithm is working. But it is necessary to actually see that the labels, all the points with the same label should do the cluster. It should be clustered. Okay. Okay. So it is also working well on the validation set too. Okay. Let's move on to the next slide. So if you have a look at the activations of the each neuron along the timeline. So here, I couldn't actually put the meaning of that picture there. So the vertical line is the time step. So at the and the horizontal line is the each neuron. I've got 64 neurons there. So you can see each row in the picture means just one single step. And each single step has got 64 neurons in the row, right? And along the timeline, right? Because some URLs are short, some URLs are long, and that's the reason why the height of the picture is different here, because each picture here is representing a different URL. So before the training, you can see that the picture in the activations, it looks like it's pretty much random. The activation is pretty much random. But after the training, you can see as you move towards the end of the time steps, which is the bottom, you can see more clear a pattern, right? So that it can make a correct decision. So, for example, these two samples have very similar patterns, and indeed these two are these two belong to the same a class of the URL. So, because you can see that two big white line on the left hand side, and after that in the middle we've got two big just black lines there. So that way you can actually see. Well, it may not mean too much to you guys, but I mean, you really want to see whether your algorithm is learning something or not, right? And that's the reason why I've got the visualization. And that's another example. And also, I wanted to know whether I can visualize the attentions. I mean, what sort of characters in the URL that you are paying attention to to make a decision. So it doesn't matter whether the actual decision is a clean URL or a crypto-locker URL. What are the characters in the URL that actually affected the decision? And if you have a look at the a vivid black characters there, so these are the ones. So for example, in the highlighted URL at the top, you can see it's a crypto-locker URL, and it actually was paying attention to the random folder name and sorry, I can't see that here. And also the random file name followed by question mark PHP, and some of those email address portion as well. So the accuracy is looking like that on the left hand side of the graph, and the loss is dropping continuously and looking like that. Okay, so what's the result? So I have trained the model for about an hour or so, and I've got about 99.92% accuracy. But after that, I it ran again. Well, this time a bit longer. I think it was just about an hour and a half or something like that. And I've got 100% on the validation set, right? So, well, so what does it mean? Is it a perfect algorithm? Perfect algorithm? No, I don't think so. So, yeah, there's one thing in the earlier training. I was identifying what was the URL. That was causing the false negative. So that particular long URL was in the test set of the crypto-locker. So it should be detected as a crypto-locker, but the model was not detecting it. But in fact, if you have a look at the URL structure, it's not a crypto-locker URL pattern. So the reason why I put that URL in the test set is because I've got that sort of a URL set from the operations team, and I simply blindly put the URLs in the test set. So in fact, it was a human mistake. So that URL should not be in that file. So what that means is that you can even do the debugging. It just tells you, the model is telling you what you've done wrong. So it's really scary. So each time you've got a new pattern of URLs, all you have to do is simply add one more folder in that structure and add the list of URLs that you want to detect, and put a name and the label, and that's pretty much it. So it's just as simple as that to do the training each time. So you don't have to do the really painful feature engineering every time. So, and that's it. Any questions?
非常谢谢双 Park 的精彩演讲。那有没有人对于刚刚的内容有任何问题 ？Okay. There's one question. Yeah.
First of all, I'd just like to thank you for your great talk.
Sorry.
Left-hand side.
Can see.
I'd like to ask, so for the embeddings, did you use like character level embeddings or word level embeddings?
Just a simple, it's a very simple one line of coding. I'm using TensorFlow. It's simply, I'm using embedding lookup. So you just simply define the weight, not the weight, the actual embedding, which is the, which is a set of numbers. So I'm going to show you the code briefly. Well, I'm not showing the entire code for, because of the copyright issue, I guess. So here, so that's one line. It's hard to see. I'm going to copy that. Oops. Just make. Okay, so that's the line there. So it's I simply, it defined a variable, that connects. Sorry, for each neuron, I have to define a variable, a tensor variable there, and simply, do a lookup operation there. So it just requires only 2 lines.
Sorry, because I'm not that familiar with TensorFlow. Could you just tell me like whether like one individual token, is it like a character or a word or a phrase?
So what I'm doing is just mapping one character to 64 numbers, and that's it.
Right, I see. So for this model, were you able to locate like which particular features or like combinations of characters were like dead giveaways that this URL was malicious? Did you find any such important features?
Can you say that again? Sorry.
Were you able to find any features, like maybe combinations of characters that were really important for the model to find whether a URL was bad or good?
Well, I'm not fully understanding, the question here, but I think what you're asking is just what, are the features that actually, the model is learning.
I mean,
is it right?
Were you able to find any particular features that were very important for the model to decide whether the URL is a bad one or a good one?
I understand. I understand that. Okay, so you can give it a try too. I mean, if you've got your own features, right? You can your own features, right? At the input, right? You can give it a try, but the main idea of the deep learning is that do not use your brain. Do not use your brain. You do not use your intelligence. Just let the model figure it out itself. So we just feed the original raw input as much as possible, so that way we are not actually missing any some important features we might miss. And that was the the model of the deep learning all the time.
Okay, thank you. I'd like to just ask one final question. Did you try your model on maybe another data set? I'm curious to see if your model parameters are transferable.
RNN is one of the models that you can use in deep learning. We got the CNN, RNN, a bunch of other models as well. So one of the beauties of the deep learning is that once you've got your working model, it can be applied. I mean, assuming that the input domain, the just characteristics of the input domain is very similar, then simply you can use the same code on the other data set too. So I actually have used that RNN in the other project as well. It was the project that you just identify the functions in the binary file. So for the Windows P file, for example, and if you do the recursive passing of all the functions, it takes a long time. And if you do the heuristics, it's not accurate all the time either. So the idea was that to identify all the functions in the file automatically using the RNN, and it was working to some degree, but it's not working in other cases because the input symbol is just only the bytes, right? Has an input to the RNN in the particular scenario, and the one single input can have two meanings, and you are assigning one single label on that, then and the model gets confused. So you have to think first whether as a human being, if you get only that piece of information without any other piece of knowledge, would you be able to tell the difference between this and that first? And if you can't do that, you can't expect the model to do that either, right? So, and you can use the RNN for any kind of sequence, but again, as I said before, the length of the sequence becomes really long, then it may not work that well. So what we have in the trend these days in the deep learning space is that we focus more on the CNN side because it's really fast to the training these days. So I think we got more and more research is being done on the CNN side, but at the same time I think RNA is still very useful and efficient for a if the sequence size is small enough. You're welcome.
因为时间的关系，我们等一下还有问题的朋友可以等一下来到前面再问讲师问题。Okay, so due to the time limitation, so let's give us the clap on.
Thank you so much.
Speaker.
Thank you.